Hello and welcome to our second video on genetic algorithms. Last video we saw the procedure, and this video we'll be walking through an example with numbers to show you how that procedure works for a real application. So going through the steps again we first have to select our chromosome length. So we will use those same 4-bit chromosome. We will say that n equals 6, set our probability of crossover P sub c to 0.7, and our probability of mutation to 0.01. And so last time our fitness function was going to be the same, f of x equals 15x minus x squared. Now we need to randomly generate our initial population. So in practice, we would use a random number generator to do all this. We are going to pretend that I've done that beforehand, and these are the chromosomes we got. So x1 sub 1 equals 1, 1, 0, 0. And we continue this down as such. Now that we have our population, we can go on to our next step, which is to calculate the fitness function. And there's a sub-step in here where we need to convert to decimals. Because we're in binary, we need a decimal number. So if we do this, we have 12, 4, 1, 14, 7, and 9. We are then able to calculate our f of x, and we get 36, 44, 14, 14, 56, and 54. The next step is to select our pair of chromosomes. So as we said before, we need to calculate these probability percentages. So we do this by first totaling our fitness value. So this is 218. We then divide each of our individual fitness values by this total to obtain our probability of being selected in percentage form. We get 16.5%, 20.2%. Both of these are 6.4%. And then 25.7% and 24.8%. We then use these to select our chromosomes for mating. So now that we've calculated those probabilities of being selected, which are reproduced in our table right here, we need to actually select our mating pair. So to do this, we pick two random numbers, this time between 0 and 100. So let's pretend those random numbers are 78 and 22. We come into our chart, you see that 78 is close to where the arrow is over here, so that corresponds to x6 sub 1, so that's our first of the pair. 22 is between the 16 and 36 here, so that means our second parent is x2. Now that we've had those pairs, we go to create the offspring using genetic operators. So with crossover, we first pick a random number, this time between 0 and 1. So let's say the first time around, we pick 0.9. 0.9 is greater than our P sub c, which was 0.7, so this means no crossover. If instead, so you do that once and move on, and this would then imply that S6 sub 1 prime is simply equal to X6 1, and X2 sub 1 prime is equal to X2 sub 1. If instead the number that was selected was say 0.53, this number is less than our probability of crossover, so we do have crossover this time. So now we have to pick another random number. This time the random number needs to be between 1 and 3 because we have 3 points of possible crossover. So let's say that 2 is selected. What this means is if we write out our values, so x6 was 1, 0, 0, 1, x2 was 0, 1, 0, 0. The 2 means that we go to our second after the second gene, and we break them here. This top part now comes below, this bottom part comes up. So this means that x61 prime is now equal to 1, 0, 0, 0, and x2 sub 1 prime is now equal to 0, 1, 0, 1. If this number had been a 1, we do the same thing with splitting here after the first set of genes. If it was a 3, same thing with splitting here after the third set of genes. Now that a crossover is complete, we look at mutation. And again, we select a random number. So we do this once for each of our 2 offspring. So say for the first time, we select the random number as 0.21. This is greater than our mutation probability of 0.01, so we have no mutation. So now we move on to x2 and we select a new number. Say this time it's 0.008. This value is less than our probability of mutation, so mutation does occur. So we need to select a random number now to determine which gene mutates. We have 4 genes, so we select a random number between 1 and 4. Say, for example, we've selected 3. So we come down here to our x21 prime, and we go to the third gene, and it switches from 1 to 0. So the mutation now makes us create x2 sub 1 double prime, which is now equal to 0, 1, 1, 1, because this third gene has mutated. Again, if we had selected 1, then this 0 would become a 1, and same thing for 2 and 4. Now that we've completed our crossover, we have our 2 offspring here and here. So with those offspring now in step 7, we assign those to the new population. So our x1 sub 2 is now equal to x6 sub 1 prime, which was 1, 0, 0, 0. Our x2 sub 2 is equal to x2 sub 1 double prime, which was 0, 1, 1, 1. In step 8, we need to repeat this. So we do the same procedure. We would select 2 parents, go through mutation and crossover. We would select x3 sub 2, x4 sub 2, and we will pretend that we did these and say that these are equal to 1, 0, 1, 1, and 0, 1, 0, 0. We need 2 more, so we go through steps 5 through 7 again to obtain x5 sub 2 and x6 sub 2, again going through crossover mutation, and we create, say for example these become 0, 1, 1, 0, and 0, 1, 0, 1. At that point, this now is our new population, and we start to go through the process again. So we would convert these into decimal values, which are 8, 7, 11, 4, 6, and 5. We would then calculate these for f of x, where the first one is 56, the second one is also 56, then we have 44, 44, 54, and 50. So we can already see that we're approaching our optimal value up here, and that all the parameters have increased. We will continue these steps going back to step 4 as needed until we've reached our termination criterion and we've found the solution we've been looking for.